Welcome back. So I'm really excited today to tell you about Gauss's divergence theorem. This is one of the most important results in all of vector calculus, and it is probably the primary building block of how we derive conservation laws from physics, from science, conservation of mass, momentum, and energy, and translate those into partial differential equations. So I'm going to walk you through this theorem kind of with pictures, with words, with math. So the idea is that we have some volume V, and we're going to say that this has a surface S, and that there is some normal vector kind of at every point on the surface of this volume. And so what Gauss's theorem does is it essentially tells us if we have some fluid flow, some vector field, I'm just going to draw some vector field kind of going throughout all of space like this, and my vector field I'm going to call F arrow. So if I have that vector field and it's carrying, mass or momentum or energy through this volume, Gauss's divergence theorem is going to allow me to compute how much of that material is kind of fluxing through the surface of this closed surface, or what is the rate of change of that material in this volume. So it's a really useful way of doing essentially accounting of physical quantities that we know are conserved, like mass, momentum, and energy, and using those to get quantitative expressions. Now, one of the things that I think is really important is intuitively motivating why we want Gauss's theorem. So when I learned about this, it was essentially just written down as a mathematical fact, and it was proven. And I think that's almost a crime not to tell you all of the cool physical applications of Gauss's divergence theorem. So I'm going to write it out in words, give you the mathematical expression, and then show you how we actually use this to compute partial differential equations. So this is one of the lectures I'm most excited for, because I think this is going to be a tool set or a tool in your arsenal that you're going to use for the rest of your career. This is a really powerful way of thinking about the world. I mean, it has Gauss's name in it. If it's Gauss's divergence theorem, it's probably the best divergence theorem. Okay, so let's get started. So I'm going to start in words, so kind of words. And I'm going to write this out somewhat slowly, and then we're going to write out the math expression. So in words, what we're saying is that the flux of a vector field, and our vector field is F, right? The flux of a vector field F out of a closed surface, so through or out, let's say through a closed surface. And this closed surface is S, okay, the perimeter of this volume, S. So the flux of a vector field through this closed surface is equal to the integral of the divergence of that vector field throughout the entire volume. So I'm going to say this again and write it. The flux of our vector field through the surface is equal to the integral of the divergence of our vector field, the divergence div F, over the entire volume. And I'll just write it here, over the entire enclosed volume V. Okay, so this is a bit of a mouthful, and what I'm going to do is I'm going to walk you through what this statement means, why it's important, and we're going to translate it into a mathematical expression. So maybe I will kind of almost start with the mathematical expression, and then we'll go back to what these words mean. So, okay, the flux of a vector field F through a surface, and I'm going to write this out in math. Maybe I will write it in blue. So the flux of our vector field through this surface is going to be a surface integral. So I'm going to integrate over my surface S. And the flux is essentially how much of F is pointing in the normal direction. added up over every little surface element. So if I want to compute at every point how much of f is being kind of carried out of this volume, what I do is I take my f vector and I take my normal vector n, and I dot them together. And that tells me how much of my f component is in a direction that will actually take me out of this volume. So let's think for a minute. If my f vector field was just swirling around in this volume, kind of going around in circles, and it had no component that was perpendicular to the volume, then nothing would be carried out of this volume through that vector field. It would just be kind of recirculating, but nothing would be leaving. And that dot product of f, if it was tangent to the normal, would be 0 dot product with n. And so the way we say this is the surface integral of our vector field f dotted with the normal integrated over that volume, over every little area element on the perimeter of this. So this is the flux of the vector field f. This is literally the definition of what I mean by the flux. This is how much stuff is being carried out of the volume. It's this. We compute how much of f is pointing in the normal direction using the dot product, and we integrate that up over the entire surface, and that's how much stuff is leaving the volume. This is basic accounting. This is the only way stuff can leave the volume, okay? Unless we believe that stuff can be created or destroyed inside the volume, okay? So if our quantity like mass, momentum, or energy can't be created or destroyed, and it's conserved, then this is a basic accounting of how much stuff leaves through that surface S. And so we call this the flux through S, the flux through S. And this is like a definition of the flux. And what Gauss's divergence theorem says is that this flux, this might actually be kind of a pain to compute. Maybe I don't want to do the surface integral. What this is equal to is a volume integral. So we'll do a triple volume integral over the entire volume of the divergence of f, of div dot f dv. And this is extremely useful. So what this says is that these two quantities are completely equivalent ways of computing the flux through some volume. And this is for an arbitrary volume. It doesn't matter what size v is. It could be a skinny little rod. It could be a sphere. It could be, you know, a little hockey puck shaped thing. It doesn't matter what this volume is. This is always true as long as f is a continuous vector field. If it doesn't have like sharp, abrupt changes or shock waves, then this is going to be true. This is Gauss's divergence theorem. And this is really important. So I'm actually going to box this off. This is super important. This is Gauss's divergence theorem. We'll put some stars next to it just so that we remember that this is, you know, really, really important result. OK, so I'm going to restate why this is true. I'm going to show you some intuition of why this expression should equal this expression. And then we're going to use this to actually compute some real conservation laws and translate those into partial differential equations. Okay? Things like the mass continuity equation or the Navier-Stokes equation. Good. OK, so why do we think that this volume integral of the divergence of f should equal the amount of stuff being carried out of f? So I'm going to draw another little picture here. I'm going to try my best to duplicate this so that we can play around. OK, so that's roughly my volume. And what we're going to do is we're going to chop this up into a number of little boxes. So I'm going to chop this up into some boxes. And I'm not, you know, a fantastic artist, so we're just going to use a few boxes here. And what we're going to do is look at the divergence in each of these boxes. So in your imagination, imagine that this is a really fine graph paper with, you know, millions or trillions of boxes. And you could take the limit as all of those boxes become infinitesimally small. That's what we're going to do. And we're going to look at the divergence at every little grid box in this graph paper representation. So at every little point here, what I'm going to do is I'm going to draw a representation of the divergence. And what we're going to have is that maybe I have, you know, some positive divergence here and some positive divergence here. Let's say my flow is kind of, you know, expanding. and some positive divergence. Okay, I'm just going to draw this. I'm not going to draw any of these negative because it's a little harder to visualize. And I've got this guy here. Now the idea is, and this is, again, this is requiring that my vector field F is continuous to do the divergence theorem, to kind of take this limit as all of these grid cells become infinitesimally small. And the argument I'm about to give you is the following, okay? And I really like this picture. It just looks super cool. So these pink sources, the way I'm drawing them here, these are the divergence fields locally that are induced by this flow F. So this F might be doing something complicated. There's some complicated physics, Navier-Stokes fluid flow, whatever. And this is the local divergence at every little point. Now what we observe is that if I really do assume that this vector field is continuous, and I make this grid infinitesimally fine, then these neighboring boxes, kind of the positive upward component of this flux and the negative downward component of this flux, should cancel each other out. Because if I make my boxes small enough, the flow is basically identical in neighboring boxes. And so the upward component of this pushing on the downward component of this cancel out. And so you actually get this kind of cancellation of all of the inner boxes. Every box that shares a wall, those two neighboring forces are going to kind of cancel each other out. And the only thing that you're going to be left with is this kind of thin perimeter of all of the divergences that don't have a neighboring grid cell. So kind of all of these little boxes that are pointing out, this is the only thing that's left when I integrate over this volume. Okay, so I'm going to say this again. When I integrate all of my divergences over this volume, when I integrate all of my divergence on this volume, all of the inner grid cells kind of cancel each other out because of the continuity of F, because F is a continuous vector field, and I'm making these boxes infinitesimally small. The right vector and the left vector on neighboring grid cells cancel each other out, and the up vector and the down vector on neighboring grid cells cancel each other out. And so we only have this thin perimeter right on the surface of our volume that don't have divergence vectors that are being canceled out. And you'll notice that if I integrate these along, that looks a heck of a lot like my flux through the volume. So this is a very cartoony sketch of why Gauss's divergence theorem is true. It's because I can integrate this flow kind of dotted with the normal along the surface, or I can compute its divergence everywhere throughout the volume and just add up all of those divergences. The ones in the middle will cancel each other out, and it will leave kind of something that's equivalent to this integral on the perimeter. So that's a really useful, in my mind, kind of cartoon of why this is true. Okay, so let's. The way I talk about this when I'm teaching this in class, this is essentially just accounting. This is bean counting of some quantity being flown through a vector field. And so as long as you can count things, these arguments have to be true. The stuff coming into a volume has to equal the stuff coming out of a volume, unless you have sources that are kind of creating things or destroying things inside the volume. Okay, good. And there's a lot of ways you can compute with this. So for example, if I want to compute the volume of an irregular shape, I can create a vector field that has divergence 1, and I can integrate that vector field all along the perimeter of my volume. I'm going to say that again. If I want to compute the volume of an irregular object, all I have to do is create a vector field that has divergence 1, and then I integrate that vector field along the perimeter or along the surface of my volume dotted in the normal direction. That will equal the volume of that object. So that's kind of a neat application of Gauss's theorem, but that's a little esoteric. What I really, really, really want to show you is how we can use this to derive partial differential equations. So let me just say Gauss's divergence theorem for PDEs, for partial differential equations. And this is really exciting, okay? So all of our modern physics, all of kind of, the textbook equations that you're used to seeing, the Navier-Stokes equations, Maxwell's equations, almost all of our physical laws boil down to a conservation of some quantity in some volume using Gauss's theorem to derive a partial differential equation. So it's an extremely, extremely powerful way of mathematically quantifying physics, and that's what I'm going to show you right now. So we're going to look at Gauss's theorem for the conservation of mass in a volume. Okay, so we're going to specifically look at mass conservation in a volume. And we're basically assuming that we have some fluid flow. Maybe we're in the Gulf of Mexico. Maybe this is the flow in the ocean. And maybe I have some oil spill at some point in the Gulf of Mexico. Maybe that's what this volume is. Or maybe there's some spill here. And we know that that is a conserved quantity. There's not more or less, at least in the short term, as it flows through. And so we want to somehow quantify this conservation of mass in our volume. So here's what we're going to do. We're going to say that our total mass, let me see, I want to write that here. So our total mass in the volume equals the triple integral over V of the density rho dV. Okay, so I'll just say rho is the density. So the density of whatever my fluid is, if I integrate that whole, that density over the entire volume, I will get the mass in that volume. And so the rate of change of that mass in the volume is equal to how much of that mass is being fluxed out of that volume through the surface integral. So that's what I want to write down. This is the basic conservation I want to write down. So so ddt of this integral, which is rho dV integrated over the volume, this is the rate of change of mass in my volume. So maybe mass is being carried out of my volume, maybe mass is coming into my volume, and it's happening because this vector field, this fluid flow, is either carrying mass in or carrying mass out. And so this rate of change equals, the only way that mass can enter or leave this volume is through it being carried out through the boundary by this flow F. So this would equal minus the integral through the surface of my mass that's being carried out through the normal direction ds. And I have this minus sign because essentially if I have a positive flow carrying mass out of my volume, if this F dot n is a positive thing carrying flow out, then that is a negative rate of change of mass inside the volume. So the rate of change of mass inside the volume is equal to minus how much of it is leaving the volume. And again, this is the only way mass can leave the volume, is that if it's carried out through this flow kind of normal to that volume. Okay, so this is the basic setup. This is, again, just accounting. This is just counting the mass in my volume here and counting how much mass enters and leaves my volume here. Good. But what we want, this is a triple integral and this is a double integral. And what we want is to somehow write these in the same triple integral formulation. So I want to convert this into a triple volume integral. And I'm going to use Gauss's divergence theorem to do that. So we're going to turn this into a triple integral by using Gauss's divergence theorem. And the way we do it is as follows. So we're going to say this quantity here is equal to minus the triple volume integral of the divergence of this quantity, right? So the surface integral of some flux dotted with a normal is equal to the volume integral of the divergence of that vector field. So this is divergence of rho f dv. And remember, rho, my density is just a scalar. It's just a number at every point in space. and F is a vector field. It's my flow that's carrying this mass in and out. So now I have an apples to apples kind of comparison. Before it was apples and oranges. I had a volume integral and a flux surface integral. Now I have a volume integral for the rate of change in time of my mass equal to this kind of spatial divergence of rho times my vector field F. And so what's really neat about this is that I can move this over to the left-hand side, and now I can put everything under the same triple volume integral. And I'm going to move my ddt inside of here, okay? And this is really going to be a partial of rho. Rho is a function, let me write this down. So my density rho is a function of space, let's say x, y, z, but also of time. Okay, this density might be changing. I might have a compressible fluid. You know, if I'm flying a jet, the air is compressing and the density is changing as that wing or the nose or whatever is hitting the air. Okay, so sometimes this can change in space and time. It can vary. And so what I'm going to eventually get when I bring this all under the integral is that I have a triple volume integral of partial rho partial t, the partial derivative of rho with respect to time. Now this minus, when I bring it over, becomes a plus, plus the divergence of rho times my fluid velocity field, all of this dv equals 0. So this is pretty special, okay? This equation here essentially accounts for all of the change of mass due to like the mass changing in time, things fluxing through the surface, and things like that. And when you add that all up, it has to equal 0. This is a statement of conservation of mass. Now, here is one of my favorite parts of this whole story of how you use Gauss's divergence theorem to derive partial differential equations, is that this is true for all volumes. For all volumes V. This is true if I had a big volume V, a stretched out volume V. It's also true if I take my V and I take the limit as it becomes a teeny tiny little delta V. This is true at every little patch in space. If I shrink my volume down to that little patch in space, this is still true. And the only way that this integral can equal 0 for all volumes is if the thing inside of it equals 0 everywhere. And so this is how we derive our partial differential equation. This thing inside has to be equal to 0 for this volume integral to equal 0 on all volumes. And so then we finally get partial rho partial t plus the divergence of rho times my vector field F equals 0. And this is called the mass continuity equation. Mass continuity equation. And it's one of the fundamental equations in fluid mechanics. This is the equation that quantifies conservation of mass in a flowing fluid, in the air. When I'm speaking, air is moving, but it's still, the mass is conserved. This room, mass is not being created or destroyed, and so this equation is true everywhere in space and in time. Okay? Even if I have a jet moving through, even if it's a compressible fluid flow, this is still true. It is only not true when my vector field F is sufficiently, or my density rho, is sufficiently non-continuous. If it has a really sharp step change in space or in time, then these derivatives don't actually make sense. They would go to infinity. And I can only represent kind of the integral effect in a control volume that's large enough to include that discontinuity. Okay? So what I'm going to do, I'm going to take a step back and summarize. And I think in the next video, I'm probably going to dig a little bit deeper into this mass conservation equation and show you what happens, for example, if I have an incompressible flow. If my density is a constant, then we can get specific we can derive specific quantities that have to be true for this fluid flow F. Okay, but let's talk about the whole pipeline here. If I have physics is generally written in terms of conservation laws. We have conservation of mass, conservation of momentum, conservation of energy. Newton's second law is essentially a statement of conservation of mass, conservation of momentum, okay? The rate of change of momentum is equal to the forces applied to the system. We can encode those conservation laws through integral equations like this. We literally count how much stuff we have in a volume and how much it changes in time. And we say that the only way that the amount of stuff in that volume can change, that mass or momentum or energy, is if it enters or leaves through the surface of that volume. So I have a volume integral for the rate of change of stuff equals a surface integral for how much stuff enters or leaves through the boundary. And Gauss's theorem, what Gauss's theorem allows us to do is turn that surface integral into a volume integral. So now I can kind of use apples to apples. I can add up everything under one common integral. And I now have this partial derivative expression that has to equal 0 everywhere over all volumes. And again, if the quantity I'm adding up, if my mass and my momentum or my energy and my fluid flow are continuous, smoothly varying in space and time, then this is true for all volumes, and I can get rid of the volume integral, and I get my partial differential equation. So this is how most of the PDEs that you're used to from classical physics are derived, is by writing down a conservation law and then using Gauss's theorem to kind of simplify that conservation law into a single expression under a common volume integral. Okay? Now, again, this relies on some continuity. That's why it's called the continuity equation, because this relies on rho and F being continuously varying. They can't be really, really sharp shock waves in the system. So if there's shock waves in the system, other interesting things will happen, and I'll show you that in a little bit. Okay, awesome. Thank you, and stay tuned for kind of the next video on this.